Okay, so I'm going to briefly talk about tries, and I'm going to talk about ways that you extend these and some of the other ways that they get extended to what's called a suffix tree and a suffix array and different ways you can use those. And that's going to be in the video. But there's a basic data structure, and I don't think that you generally encounter this in 411, although maybe you do, but the term for it, and I pronounce it trie, T-R-I-E. I don't know if that's the right way to pronounce it or not, but that's the way I learned it, so that's the way I pronounce it. Is this something you learn in 411 or not? Does that look familiar to anyone? Okay. So a trie, it's kind of an interesting data structure. It's basically a tree, and it's a tree that you use for dictionary operations. And it makes it really useful to do certain types of calculations. Now, in many cases, the thing you are looking for, there are other ways that are potentially capable of doing it more efficiently. For some of the applications, for others, this is kind of the right way to go. So the idea is we are going to have a node, some base node, and again, our theme here is strings. So we're wanting to store strings along the way. And so if we have a string, we're going to have each letter of the string is going to be based off of a child, is going to be a child node here. And so this is going to run from A all the way over to Z. Okay, and if you need to distinguish between upper and lower case, then you would have to actually have 52 different children instead of 26. Okay, and if you need punctuation, you might have to increase it more. But generally, you just have the 26 things because you don't care about capitalization or punctuation or any of that. Okay, and so if I have something that is a word like at, I would go follow the A edge off of the base, and then I would follow the T edge off of the A, and then I would mark that as a destination node. And what that would mean is that the string at is a string that I care about. And if I need to store information with that string, I can store it in that node. Okay, this makes sense so far? Okay, so if I want to, I'm going to switch to a new screen. If I want to, I can enter a lot of words into a trie like this. Okay, so give me some fairly simple short words, just anyone. Apple. Okay, that's not that short, but it'll work. And cat, great. Yak. Let me get yak. Let's go with car. What was it? Run. Okay, okay, that's good enough because I want to pick some other ones here. How about the word be and the word then? Is that a word? It doesn't look right. Then, huh? Yeah, like I've been there. That's car, cat, call. Okay, that's enough. Okay, so let's see what the trie would look like here. So we have our base node, and each thing that we implement, each thing that we create in here, we're going to create children off of here. So the first one will have A followed by P, followed by P, L, E. Okay, and we'll say this indeed is one of the words that we have. Okay, the next one is cat. So we will have C, A, T. We'll say that's a word. Okay, the next one is yak. So we will have Y, A, okay. Call that a word. Okay, the next one is car, C-A-R. So that's a word. Make sense so far? The next one is run. Okay. Then I'm going to skip the B's for just a minute and go with call. So we'll have C-A-L-L. Say that that's a word. And then I'm going to do B out of order. I'll just do it down right here down the middle. So we have the word B, E, E, for the word B. And then we have the word B-E, which is that one. We have the word B-E-E-N, which is that one. Okay, so basically we're going to just mark which nodes exist and which ones don't. And now, why is this useful? Like how could you make use of this? Okay, so one thing you can do is you can use this to test and check whether a word is in your dictionary or not. So let's call this your dictionary. And you say, is yak a real word? And you would follow Y-A-K. And indeed, you would see that you end up on something that Y-A-K is a real word. And you say B-E-E-N, and you say Ben, sure, that's a real word. Okay? Make sense? Okay. However, there's other things you could do. So let's say that you are doing typing. And you're entering a Google search and it wants to give you, here are some likely searches that start auto-completing the word that you're typing out. Okay, so let's say that you start typing C and then A. It can keep track of what are the words that are below any one node in there. And it can actually keep track of an ordered list of maybe the 5 most popular things at each node along the way. So when you get to CA, it says, well, CAT is the most popular word, and CALL is the second most popular, and CAR is the next most popular. And then you type an L, and it goes down to that node, and it says CALL is the most popular. And maybe there's some other words like call, I, and call, I-N-G, calling, okay, or C-A-L-L-E-R for caller, okay, and basically the more words you have in here, the more you can keep track of. And at all those intermediate nodes, you can keep track of what would be there along the way. Does that idea make sense? Okay, so if you have a trie, it actually gives you a way of sort of doing all of this storage of data that you wouldn't have otherwise. You can store all sorts of information in there. You can store how many words in your dictionary might start with a certain thing. And then when we talk about, and this will go off to what's on the video, when we talk about suffix trees and suffix arrays and stuff like that, they're sort of based on this idea. Okay, they're implemented slightly differently, but they're based on this idea, and you can perform all sorts of things based on suffixes along the way. So what I wanted to show you the code for, and it is something that you'll be able to use in this week's problem set, at least if you modify it. It won't be just straight code like this. Or not this week's problem set, the one for next week, is to show you how you might implement a trie. And there's different ways of doing it. I'm not going to promise this is the most efficient of all of them, but it is a method for doing it. Okay, so let's go ahead and create something that's trie.cpp. And I'm going to include IOStream and stream. Okay, so I'm going to create my main file. And so I think the way I'm going to have this one work this time is I will just read in words and enter them into the trie, and then I will output the trie at the end. Okay, so seem reasonable? Okay, so I'm going to say that I have a string s, and see if I'm doing stuff here correctly. Yeah, so while true, so I'll just keep reading in words until I hit some word that I don't want anymore. Actually, hang on 1 second. Let me make sure I don't miss people. Okay. Okay, so while it's true, I will read in a string s, and I'll say if s is equal to what do we want to be the word to say we're all done? Done. We'll say done. Done. If S is equal to done, then I'm going to break. I'm going to stop reading stuff in. And then otherwise, I am going to insert S into the trie. Okay? So the way that the trie will be is I'm going to create, it's going to be a tree, so I'm going to create a node class, and I'll have the base, the root node. So I'll have a node, and I'll call it my trie. And so I will just say trie.add S. So I'm just going to add S into the trie. And then at the end of all of this, I might go ahead and say, here's the dictionary. And I will call something called trie.printout. Okay, sound good? So that's going to be my code. I'm just going to read in stuff S. I'm going to create all of that. So I need to create a node class. So class node. And I'll just make everything public to make my life easy, but that's generally not the way to do things. Okay, so what do I need in each part of the node? What's the information that I need to keep? I need to keep a Boolean value that says, is this a node that is a string? So I'll keep track of a Boolean that says is in, something like that. Okay. And then I'll also need to keep track of a list of children. And how many children should I have? 26. Yep, 26 of them. Okay, so this is going to be a series of pointers to nodes, I guess. And these will be the children, and it will be of size 26. Okay, so I'm going to use pointers here. There's other ways to do it. I grew up using pointers, so I still like using them. Probably better to avoid them in a lot of cases, but it's easier to do that for me. So, okay, so we're going to need to have a couple of things. We ought to create a constructor function. So something that just initializes this. So isIn equals false. So if we create a new node, we don't want it to be there. And let's see what else. Yeah, we probably want to initialize all of the children nodes to null. So okay, so there's a constructor. So all we did when we create a node is we say this node is not yet a string, and we say all of the children are going to be null. It has no children at the beginning. Okay, so no pointers to any other nodes at this point. Okay, so we needed two things. We needed one that would add. And we needed one that I think the one we used was printout. Okay, I think those were if I remember correctly, those were the two commands that we had down below. Yes, add and printout. Okay. And just so that I can see if stuff is working, let me just see if I've made any errors so far before I go any farther. String, man, I am tired today. String. Okay, so that seems to compile at least. So let's go ahead and run this. and then I'll say cat, and it would be adding cat and car and call, and caller. Okay. So that's the idea. And then I think it was, I typed done, and it would say printing out. Okay, so things seem to be working. You know, the skeleton code that I've put together seems to be working okay so far. All right, so let's go ahead with adding. So if we want to add a string to the trie, what we need to do is basically go character by character and work our way down the trie. Okay, so we're going to take a look, first of all, I guess, if, and I'm going to do this recursively, right? So if I'm in a node and I want to add something to one of my children, I'm going to take the first character and I'm going to like pull it off, and then I'm going to go down to that child. So if the first character is C, I go down to the C child and I put AT, the word was cat. Or if it was car, it would be AR. Or if it was call, it would be ALL. So I'm going to strip that first character off, and I'm going to pass the rest of the string down. Okay, so if I ever run into a case where the length of the string is 0, that means that I've kind of run out. I'm actually at the destination node. I don't want to do anything else. So I set isIn equals true. And I go ahead and I return. So I'm done. I don't need to do anything more. Okay, if that's not the case, then what I need to do is I need to pull off that first character. So I'll say character C equals S0. Okay, and I will check to see if that child already exists. So if child, and then to get this, it would be C minus A. Okay. Oh, question. Yeah. Right. So this is going to be for the current node. That's a good question. So the question was, let me admit everyone. So the question was, don't we have to pass in which node we're at? And you could pass it, so you could write this whole code that way, like where you actually march through the tree and keep track of the node you're on. So I'm writing a recursive function where you're actually in the node itself. So each node is going to keep track for itself, am I true or not? And then when it goes to the next one, it'll just jump down to the next node. So for instance, that's the reason why I'm going to, as you'll see in 1 second, I'm going to actually strip off the first character and pass the substring down to the child. The other route you could go is you could take in your whole string and you could kind of march through the string and say, I'm going to go to the first, like set I equal to 0 and increment I through the string and go down to a child as you increment I. And that would work fine, but you do have to have the node that you want there. Good question. So there's actually like two approaches you can go to. This one, I think, is a little bit easier to write. It's not necessarily the fastest because we are going to be stripping characters off of here. So there's more efficient ways of doing things because doing a substring is slow compared to just marching through a string. Okay, but one thing that we want to do is I want to make sure people understand this line. Okay, so this line says if child of C minus A. So C is the character that I have. Okay, so sorry, there's a question online. IsIn says this is a valid string. So that's like when I was doing the little example earlier and I would fill in one of the nodes red. That's like setting isIn to true. It means this was the end of a word that was in my dictionary. Okay, so this is, notice that what we're doing is to find the child. If we subtract off A, so if C is the character, all of the characters are numbered, all of the letters are numbered consecutively. Okay, starting with capital A. And remember that a character is just a short integer. It's just a 8-bit integer. And so if we subtract off A, we just get an integer that we can use to index into the array. Question? This will not be case, well, the question was, is this case sensitive? So I am assuming capital letters only. Okay, yeah, good question. I'm assuming capital letters here because I'm subtracting off capital A. If you were to use lowercase a, this becomes a little like lowercase letters also, this becomes more complicated. In the worst case, you could use all the ASCII set, 256 characters, in which case you'd have 256 children, most of which would be null. But occasionally, at least the 52 letters and some of the punctuation and stuff would get used occasionally. Okay, but generally, if you think of it standard dictionary, you don't worry about capitalization, and so you would do this. And if you wanted to, you could always convert your entire input string to all caps or something along the way. Okay, but the point here is this is going to be a number from 0 to 25 that actually tells us which child we have. So if the letter is A, it's 0. If it's B, it's 1. If it's C, it's 2, and so on. Okay, and so if we haven't already found something that is like that, then we can set that value to be a new node. Okay, so we create a new node for that value. Okay, otherwise it already exists. Otherwise we already have a child there. And then in either way, we're going to create a new string that is going to be everything left off of the first one. So s.substring, so we can use the substring command, and we'll start at position 1, which means we keep everything there. And I believe I can just use that, and that will give me the entire length of the string from there on. And then I just say ch of c minus a. Okay, so that's the child node that possibly we just created, or it's something that we had before, and we are going to add onto that s2. Okay, so we stripped off the first letter and we added on the remainder into its child node. And that's going to continue until we eventually get to something where the string is 0, it's 0 length, and that's when we mark that the thing is true, and we're done there. Okay, so that should be the process. I'm just going to compile this and run it to make sure I didn't make any. Sure am, line 27. There. Was that the only one? Okay. And I'll just check this. Okay, so it's not actually printing anything out at the moment, but that's the idea. All right, so the other thing that I need to be able to do is print stuff out. Okay, so as far as the printing out goes, this is basically going to be just an in-order traversal of the tree. So what I can do here is I can say if is term, okay, and actually I know I'm going to have to do this. What I'm going to do is I need to remember all of the stuff that all the letters that I've had above me when I get to a particular node. So I'm going to march through the tree. I need to know like the path from the root down to where I am along the way, so I know what to print out. So I will take in as input a string s, and I will set it equal to the null string if I didn't pass anything in. Okay, so if I don't pass in a string, it's just the empty string, but otherwise it's going to be whatever I had before. So if is in, so if I'm actually at that final position, then I will want to output that one. Okay, so I go ahead and output that string if it's there, and I can get rid of this now. I'm going to keep an integer, and okay, and so now basically I'm going to look at each of my children, and for each child I have, I'm going to add that character on and recursively call again. Okay, so I will say for I equals 0. In fact, I don't need that. It's just going to be here. For I equals 0, I is less than 26, I plus plus. So I'm going to go to all the children and I'll say if child sub I is not null. Okay, so if we've actually got a child there, then I want to call it. So I'm going to say S2 equals S plus, and then I want a character that is made from I plus A. Okay, so I plus A is the character. That's what that child is. So that child is there. We have that. Okay. Yeah, you can make this. So Drew says you can make this faster by doing s dot pushback character pop back. You're right. You could in fact just push and pop off of S here. I'll say there's actually a lot of ways you could improve this quite a bit. In fact, by not stripping stuff off when you're putting stuff in, it would also be a lot faster. So, okay, but everyone I hope gets the idea. We'll do that. We'll create S2, and then we will call ch sub I printout with S2. So we'll pass in that string that we have up to this point and go from there. Okay, so let's try running this, compiling it. Okay, so let's say that we have words like cat, and call, and car, caller, dog, dog, do, gag. Okay, and now I'm done. Okay, so the dictionary is call, caller, car, cat, dag, do, dog. Okay, so indeed we got that. It was in alphabetical order because we progressed through the children alphabetically, and we always printed off. Notice we printed off the root first before we went through the children, in case it was there. And that's going to be all the words that are in that dictionary. Okay, so that's the basic idea here. Is you have a trie that lets you store this information, and then you can look it up later on. For the problem sets next week, at least a couple of the problems, you can use something like this as the base for solving the problem. You will have to modify it. It's not going to just be straightforward. It's not like you copy this code and you're done. That would not be a challenging problem at all. But they're not super challenging problems once you know kind of how to do them. Now, that's not all there will be. There will be some other string aspects as well, but those will be there. Okay, does anyone have any questions on this at this point? Yeah. Okay. The question was, do you have to make a destructor for a caddis submission? No. For good coding practice, yes, you should always make a destructor. So I didn't put a destructor in here. I probably should have, but for caddis, it doesn't matter. Well, I will say it could matter if you have something like where you're running multiple cases and you keep allocating memory. You could get a memory limit exceeded, so you might want to have a destructor in there to avoid memory overflow. But typically, that's not going to be the problem in something like caddis. But if you ever get a memory limit exceeded, yes. Other questions?